Yeah. Oh, but
can you see that?
Yes, we can see it. So
right, see where it's hidden. Present.
let's see if it works. And now I can introduce you. And I'm really happy to have here with us Fiona Pollack. She is a professor of software engineering at Kiel in UK. She is an interdisciplinary researcher, and she tries to make software engineering usable and useful. I remember discussing this with her in Dutch 2 seminar. And indeed, her work in model-driven engineering has been used, for example, in the York Computational Immunology Lab. And building on simulation as a scientific instrument, she is researching model-driven engineering support for simulation and exploring uncertainty in all stages of simulation. So today we are really excited to have Fiona here and to listen to her keynote on uncertainty models of unknown realities, modeling and simulating complex biological systems. So thank you, Fiona. The floor is yours.
Thank you, Raffaella. Yeah, it's a great honour to be invited to come and do this keynote, and I hope that I can satisfy some curiosities. I have a confession at the beginning. If the virus hadn't intervened, there was going to be some more serious research behind this this presentation. So it's a bit more speculative than I'd hoped, but I'm going to cover a variety of angles, and hopefully we can have a bit of discussion at the end. So as Raffaella said, over the last 2 or 3 decades, I've been looking at practical software engineering. I'm very academic about this, so don't ask me complicated questions about tools and things. But there's a lot of thought gone into this, and there's a lot of people involved, as you'll see. I mean, it's very definitely interdisciplinary work. So I want to start off with something that hopefully is obvious to most of this community, but a bit of a thought about what complexity is. And when we're thinking about complexity in software engineering, I would identify a number of different sorts of complex software engineering, but they all feature similar sorts of challenges in some ways. So we might be engineering systems that are complex, so command and control systems, distributed collectives, agent systems, that sort of thing. Or we might be engineering software that mimics complexity. And although both sets are really interesting, the one that I've spent more time on is the second. So I want to talk to you initially about what that involves. I give you some definitions. These are slightly contentious, and you'll find counterexamples in both areas, but I think it's worth having some ideas on the board, as it were. So complex, I think of as systems that are made up of simple components. So that in itself is contentious. As soon as you get a human or a biological system in your complex system, it's hard to see it as simple, but actually we can normally represent what we need to know about components as relatively simple machines, state machines, if you like. A complex system has behaviours at many scales. It can be observed at many scales. And essentially you have to run the complex system to find out what is actually going to happen. And I would include as complex systems literally every natural system, as well as cyber-physical systems and systems of systems where things interact, should we say, outside the computer, so that there are interactions that you can't control, can't always necessarily know or capture. And by contrast, traditional software engineering, which is becoming relatively unusual these days, is about compositions of components. So it's we tend to think of these as difficult, but each individual component is an engineered system which on its own is reasonably predictable. These sorts of systems are typically modelled and implemented on one scale. And of course, the classic part of software engineering is that we can predict or prove what happens. So we have good models that have formalisms attached, and we can do event modeling. We can prove that the right traces will occur and so on. And that would be any traditionally engineered system, whether it's mechanical engineering, civil engineering, etc. But notice that you really have to ignore or simplify the environment or the substrate, because they're only predictable when you rule out all the stuff on the left, the actual complexity of the environment in which they run and the kit on which they're run. Oh, right, I've now lost, oh, there we go. Briefly lost my ability to change slides. So what I work on is simulating complexity, or I work with people who are simulating complexity. And the contrast that I would make there is that when we're doing conventional software engineering on conventional complicated systems, or even when we're engineering that first sort of complex system, we're trying to mitigate complexity. And the classic example of this is things like fighter aircraft, where the software is continually managing the instability of the aircraft so that it behaves in the way you want it to. So there's a real use of the complexity of the aircraft. But if you can't mitigate and manage that complexity, the aircraft's not going to stay up there very long, or not in the way you want it to stay up there. And when we're mitigating complexity, we do want to prove that things will happen as we expect them to. We want to very clearly define what happens so long as the system stays within specification. And in the complex areas of conventional engineering, we want to demonstrate, for example, that risk is as low as reasonably practical, the ALOC principle. But when we're simulating complex systems, if we didn't actually incorporate complexity, then we wouldn't get the behaviours out of our simulations that we need to learn something about the reality that's being simulated. We're building systems that need to display emergent behaviour, but that emergent behaviour has to be demonstrably related to the behaviour of the system that we're trying to simulate. A number of quantum scientists have shown that in order to simulate a universe, you need another universe. And in fact, to simulate anything within a universe, you need a universe, which means that complex simulation is fundamentally infeasible. So one of the engineering skills that we have is that we have to simplify in order to be able to produce a computationally feasible simulation. And also when we're doing looking at complex system simulation, we, as you'll see in a moment, are building systems to try and help laboratory biologists, laboratory immunologists in our case, but to help with an understanding of the system. And I arguably that would be true for any simulation of complexity. So if we put all the detail of the underlying system, assuming we could, which we can't, if we put all the detail of the real system that we're simulating into our simulation, we would have no better understanding of the simulation than we do of the reality. So this is perhaps the key engineering question, is how we simplify without losing the validity of the simulation of the complex system. So I'm going to introduce very, very quickly and very simply our immunological example. It's one slide at this point. And then I'm going to tell you about work that a large group of us has done over quite a few years now on the principled modelling and simulation of complex systems. And the little logo at the bottom here, Cosmos, was our project logo. So example first, just to give us something to grasp onto. You'll see from the way I present this that it's capable of being presented as a set of simple interacting components. There's some big words, don't panic. So this is basically about cell clustering. It's called organogenesis. It's the formation of, in this case, little bits of the immune system, which inhabit the gut. It's investigated in labs in prenatal mice. There's limited lab data because anything that involves cutting up animals tends to produce limited examples, but also because the mouse in itself is a model system, and each mouse is going to be a slightly different variation of that model system. So, and I comment a little bit on data later on. The simulations take the simulation that was created by Kieran Alden, who's the first of the references in the little box here, as part of his PhD thesis. The simulation basically covers the development of Peyer's patches, which are these immune organs within the mouse gut, over a 4-day period, and it's around about 15 days before the birth of the mouse. So the simulation is simple in many ways. It gives some really, really complex behavior. There are 3 sorts of cells, 1, 2, and 3 on the slide here. LTO cells are fixed to the gut wall, they're static. I'm sorry these all have such similar names. It took me ages to get my head around which was which. Then we have these things called lymphatic tissue initiators, LTINs, and they have a limited role. They simply make contact with the LTO cells and cause a change of state. They differentiate, cause the LTO cells to differentiate, such that they have the ability to attract and hold other cells, attract and bind other cells. And the final sort of cell, which is also a mobile cell, the lymphatic tissue inducer, is attracted and bound to LTOs. And you go through a period of aggregation on the cell wall, which is a period that we're interested in this research. Then something happens which stops aggregation. That was outside the scope of simulation. It's a really interesting biological question. And the organogenesis, the actual conversion from a bunch of cells into an organ, actually happens. So the simulation purpose was around the timing of the chemokine involvement. Chemokines are just chemicals that are excreted, produced by one of these cells and either attract or differentiate other sorts of cells. We don't really need to know, as we'll see, too much about these. So this simulation, which as you'll see from the dates on the references, was done in the mid-2010s, early 2010s, was one of our examples for exploring the software engineering principles of simulation design. It uses this Cosmos process. So the next few slides just are a quick introduction to Cosmos, and very happy to talk about any other details afterwards. So quick introduction to Cosmos. It's essentially a life cycle diagram. So like any software engineering life cycle diagram, this is a set of ideal activities. It doesn't tell you how to do it or how to validate it or how to evaluate it. There's a bit of evaluation written in here. And I'm going to take you round this loop over a set of slides now. So we start on the extreme left. Before we get stuck in. Principled simulation, we're trying to do simulation which has, shall we say, inherent validation. We call it fitness for purpose. And we do that by working with domain experts and software engineers. So in this particular, in the Peyer's patch example, Kieran Alden was a software engineer, and he was working with a biological lab, which was represented actually across Europe. There was a Portuguese part and part in York, and I think most of them are now in Oxford. But these domain scientists, these domain experts were, if you like, the oracle for any information about the domain. So it's a really strong collaboration where sort of elements of trust are built up between the domain experts and the software engineers, but equally both sides has to be alert to being over trusting. So one of the things that happens when you do this sort of simulation is you put a visual front end on it, and the domain experts get terribly excited because they can see cells running around and doing the things they want them to do. And the software engineer has to demonstrate their trustworthiness by saying, well, hang on, no, all you can see is the picture. There's behavior underneath this that we need to explore. So one of the aspects of this is that there are joint decisions made on the purpose of the simulation, which is quite strict. What can be simulated and what it's useful to simulate, and how to simplify the reality. So working around the life cycle, the first thing to think about very briefly is the domain and the domain model. These terms, like any decent life cycle, get used to mean different things in different projects. But the domain and the domain model are talking about the domain expert area. So in this case, the detail of the immunology. We look at models of component behavior, but we don't necessarily see the sorts of models that as software engineers we would expect. We get a wide range of sources, documentations and notations. So here's an example. These are both taken, these are both cited in Kieran Olden's thesis and the subsequent papers as examples of the domain information. And I've pulled these together to show you the sort of things that if you're working with a biologist, you'll be given to start off with. So don't overlook the 2 citations in boxes. These are 2 of the key papers that we used for background information. And in fact, the co-authors of the top one, Vega Fernandez and Coles, were co-leads on the project. So you get a lot of, in biology and immunology, you get a lot of these sort of sketch diagrams. And the one on the left is actually a really detailed behavior diagram. It takes a bit of unpicking, and there's an awful lot of biology and bits of biochemistry in it. But this is a time sequence of the behaviors that we need to simulate. On the right, we've got some actual images taken by dyeing, using a dye on embryonic mice and then imaging. These are interesting in that they show you static structures. You think you're looking at something dynamic because they're imaged, but the dyes obviously disrupt the system to some extent. So these are not long-term. You can't use these long-term to explore the behavior of the system that you're looking at. And again, you see one of these little sketch diagrams used to situate the image that you're being given in the evidence. So this is typical domain information. And if you work in a domain, as you're unlikely to be working in immunology, if you work in another domain where you're building systems to represent something, you'll be used to these sort of expert sketches. They may be more semantically underpinned, or they may be just as vague as these. Okay, so once you've really explored the domain and the domain model, and in the best software engineering traditions, it won't be strictly sequential and there'll be a lot of iteration going on. We characterize the next step as a platform model, and this is where software engineers will begin to be more comfortable. It's essentially the iterative software engineering design for a particular platform. It involves obviously selecting the platform. It involves developing algorithms. It involves modeling the representation of the environment that the simulation will use. So there's been a shift here from the world of the domain expert into the world of the software engineer. But we have to make sure that the domain expert can still provide some form of validation, some form of oversight, and check and approve the simplifications that we're making. So this is where the interdisciplinarity is evidenced, because clearly there's a lot of I don't understand what that sentence means, or I don't understand what that picture means. Here's an example from the PPSim. The Pies Patch simulator is called PPSim, taken from Olden's thesis. It's been reproduced in various papers in various forms. This is, I think there are about 3 or 4 different software engineering styles of model used. This is the one that's used most, which is moderately conventional state charts. They've been they've been quality controlled a bit since the original thesis, but we basically got one state chart for each cell type demonstrating the behaviours and the controls of the behaviours. And please don't try to understand this. I recently did some work on the derivation of these, and it takes literally years of ploughing through these diagrams and the accompanying text to work out what's going on. They're a lot more complicated than they look. But going back to the complexity definition, you can see that we've only got sort of 4 or 5 states and a few transitions. So they are actually quite simple systems, even though they're capturing a lot of really elaborate behaviour. I'll come back to some of the detail of that briefly later. So once we've done the platform model, we've got a design, and we've got we've been working with the domain experts, so both the software engineers and the domain experts are reasonably confident that this is a good model of the behaviour that we want to simulate. Then we can create the code. So this is the point in traditional academic software engineering where you make your decisions about what the platform is and you modify your models. So in this case, we were using Java Meson, so we start looking at class diagrams and so on. This is also the point where you have to tie down your simulation environment. A common model is to use a 2D continuous grid for a 3D to represent a 3D environment. You also have to decide your temporal scales and so on, and what your agents are going to be. The coding is also implementing parameters, obviously, and algorithms, working out what operations you need to implement the algorithms. And of course, in traditional software engineering style, we're saying the simulation is a valid implementation of the platform model, which is a valid implementation of the domain model. So we're sort of inheriting the fitness for purpose as we go, but we accrete uncertainties as we go along. And just on the bottom left, another bit of work that should have been finished but hasn't been owing to viruses. Stefan Shaler from King's and I have been starting to look at something we promised to do about 15 years ago, which was to explore model-driven engineering as a robust way of going between platform models and simulation platform. So you could concentrate on some of the details in this slide, the implementation of computational parameters and algorithms, for instance. So platform to simulator. The PPSim simulator was created in Java Meson. It's a Java agent platform. We had class diagrams. Again, don't bother reading the information, but we've got essentially agents which are subclasses of other agents, as you might expect. Interestingly, these diagrams, so Kieran Alden created one, he did the implementation, we reverse engineered a class diagram, and I also systematically derived a class diagram working through all the information we had. And actually all the variants, the class diagram, this is just academic fun and games, all the variations come out remarkably similar, but they highlight some interesting differences between taking a model-driven engineering, a sort of translation approach, and the traditional approach to coding, which is use the design as inspiration rather than as a rule base, as it were. The last part of Cosmos, which actually attracted a lot of interest from domain scientists, both within this particular project and in others, is what happens after the simulation. One of the inspirations for Cosmos back in the mid-2000s was the realization that an awful lot of people were building simulations of bits, typically bits of biology, but bits of all sorts of things, and making conclusions about the behavior of the actual system that were quite often invalidated by the assumptions and the steps that they'd gone through between the domain and the results themselves. So we added in a results model. And this is not so much a model in the way that software engineers think of them as a recognition that results from a simulation are not results on the domain. And I've marked the gap here as the reality gap. So we have to use all the understanding that we've generated in working through the 4 outside boxes here in order to interpret the results back to the domain. So given all our assumptions and our design decisions and our simplifications, and that's represented in the diagram, Cosmos diagram, as the research context. Again, this is not a formalized model. It's a repository of everything you learnt on the way. So after millions of runs, and I think it was 500,000 runs to test the simulator and then more to get statistically relevant data, the Piers Patch PPSim project produced some really interesting results that amplified what was known in the laboratory. But actually the most interesting part of this is the last bullet here, which was it identified specific things that could be tested in a laboratory, focusing down the attention of the lab scientists into some questions that they could answer in the laboratory. And the paper cited here from Frontiers in Immunology was the presentation of both the model and the laboratory work, and the demonstration that the model had indeed filled in a gap in reality, and that had been demonstrated experimentally. So that, in a sense, is the introduction. It's the first half of the talk. The rest of the talk is, as I said at the beginning, a bit more speculative. And I'm taking you off in a direction that I've been trying to go for about 3 years now, of exploring uncertainty. And I know some of the people on the call are probably aware of some of the work that's been kicking around in this area. And entirely coincidentally, although they've converged to some extent and diverged to other extents, this very much parallels in time work that's been done at the Object Management Group, the OMG, around defining uncertainty in software engineering modelling, and work that's been done in a much more interdisciplinary context, looking at modelling complex systems and environments. And the deep here is an allusion to the deep uncertainties in some of these environmental projects. So I'm going to touch upon, I'm going to use PPSim as an example and get quite a lot of, it's not detailed. I'm going to get into quite a fine level of detail, but without going into any unnecessary immunology, partly because I'm not an immunologist, I'm a software engineer. But I'm going to talk a little bit about the sort of different sorts of uncertainty, what we did with some of the uncertainties in PPSim, and then some of the things that our Cosmos process encourages that we used in PPSim to try and manage the uncertainty. This is still all very uncertain. So exploring uncertainty in PPSim, anyone who feels like going and reading Kieran Oldham's thesis, he has a lot of coverage on uncertainty, which back in 2012 was really quite unusual. So there's a question, what does uncertainty actually mean in a complex simulation? To some extent, or to a large extent, I guess, it means, can we give assurance on our results, even though they can't be checked by targeted experiments? Can we, for example, say can we give bounds of confidence on our results, or something that equates to bounds of confidence? How do we actually go about testing a complex system simulator, which is going to give different results for every variation of the random number seed, for example? And as I go through this, you'll see that the management of uncertainties in simulators is intrinsically linked to the validation approach, which earlier on I contrasted to software engineering. The typical techniques that are used to validate, I'm hesitating because validation to most computer scientists mean either it's valid or it's invalid, it's a Boolean. Whereas when we're talking about complex systems and simulations of complex systems, it's much more of a continuum. If all our initial assumptions hold, and if we've actually done a fit for purpose simulation development, then we can say that these parts of our model are fit for purpose in these particular contexts. But if the domain scientists made a new discovery and we had to adjust something in our model, we'd have to start again with the demonstration of fitness for purpose. So I habitually say fitness for purpose rather than validation. I'm saying validation here to hopefully tie in with the more conventional software engineering language. So typical approaches to validation for making sure that your complex simulation sufficiently mimics the real behaviours or the observed behaviours of the reality would include calibration, which is repeatedly running the simulator with different parameter values from known ranges of parameters, for instance, until you get behavior that looks like the original behavior, the system that you're simulating. Sensitivity analysis, which Kieran Alden, the author of PP-Sim, and a couple of other PhD students, including a guy called Mark Reed, who's now out in Australia, did a lot of work on sensitivity analysis, drawing on best practice in various other areas. So you're not just testing to see if one particular parameter is oversensitive or not sensitive enough, but testing combinations of parameters until the software engineers and the domain experts both agree that what is in the simulator is biologically credible. So it's a really interesting and very, by computer science standards, very vague approach to validation. And I put visual inspection by domain experts here as well, as I alluded to earlier. If you show an immunologist a picture, a visualization, moving pictures of the cells moving around and forming clumps, they really do get very excited. But they can also they're really attuned to spotting odd behaviors. So if you have a particular sort of cell or a particular situation in which cells are not doing what they would expect, they're quite good at spotting those. Working out why they're not doing the right things is another question, and is almost as complicated as trying to work out how to do a simulation in the first place. So we go through this process of calibration and sensitivity analysis and a bit of visual inspection, but we still don't really know what's uncertain, partly because the real system that we're simulating is also uncertain. We can only observe it in restricted ways and over restricted time frames. So we've got uncertain uncertainty. Guess what? We've got unknown unknowns. I pulled together here some of the categories of uncertainty. Now, having been dabbling in this area for 4 or 5 years, I'm aware that the discussion of uncertainty covers many disciplines, and there's a certain amount of agreement on types of uncertainty, but this is by no means comprehensive and by no means agreed, and I'm sure many of you will be aware of other forms of uncertainty that don't really come under these headings. I'll just work quickly down these and then explore some uncertainties in a little bit more detail. So behaviour uncertainty. So biological systems are not things that you can take apart and observe, because they stop working as soon as you start to take them apart, like most complex systems. So there are lots of behaviours, even where we understand the chemistry and the physics, there are lots of behaviours that don't seem to do what you would expect. There are unknown details of behaviours. And fundamentally, in our situation, that's why we're simulating. If we knew what all the behaviours in a Pious patch formation over the relevant 4 days prenatal mouse, if we knew what everything was, we wouldn't need to simulate it. We might simulate it just to check our ideas, but the simulation would be relatively easy to develop. Ours isn't. We really don't know enough about the behaviours. In a sense, the simulation is checking the behaviours as well as trying to get some data. But what are we checking against? Aleatory uncertainty is on pretty much every list of complex systems uncertainty. It's the inherent complexity, the fact that the system never does the same thing twice. And the universal solution to this seems to be to do statistical tests. So you do multiple runs. So some of the PP-Sim runs have gone for thousands of runs overall. They've done millions of runs of the simulator. So any result is a statistical distribution. Parameter uncertainty. I'm going to look at parameters in a moment. Things like which cells go into the system sound fairly simple. Things like which things on the cells have a measurement sound really simple, but actually trying to unscramble the biology into key factors in behaviours is far from simple, and often involves a lot of time and discussion, a lot of evidence searching. But it's not just identifying what the components are, what the parameters are. It's also that we end up collapsing parameters. And again, I'll show you that in a moment. And understanding what the effect of that is, and has it introduced more uncertainty? And then we've got the perennial measurement uncertainty, complicated, of course, by the fact that measurement in live biological systems is always pretty prone to uncertainty. And of course, every mouse you look at, if we're looking at prenatal mouses, every mouse embryo is slightly different. So there's lack of consistency across instances. You're always looking at distributions rather than absolutes. Different labs, different lab mice are subtly different. So you might get measurements in 3 different papers, but they're all from different contexts. You won't have enough measures to know, if you imagined that those eventually would form a nice normal distribution, you can't really tell from these small, relatively small number of measures that you have, which of those labs observations are from the tails of the distribution and which are from the main part. Clearly, you would expect to have more from the peak of the distribution, but that's not always the case, and we don't know. One of our great entertainments, which has come out of a number of these simulations, is unrecorded rationale. I think it was PPSim, it may have been one of the others, where a particular parameter was causing problems. So they asked the domain experts what the rationale for this parameter was. And the domain experts eventually tracked down that this had been assumed in a paper 25 years ago and never tested. Biologists will state with absolute certainty, because for 25 years, this has been what was believed about something. But when you trace back, it's never actually been tested. So we have a real mishmash of Donald Rumsfeld's known unknowns and unknown unknowns, but we don't necessarily know which of them are actually unknown unknowns. Just to get back to reality a bit, when Kieran Alden was talking about Piers patch uncertainty, some of the things that he actually covered were the fact that we're using a 2D representation. And the justification for that goes something like, we checked this with the domain experts and they couldn't see any reason why it didn't work. Clearly, if we had 10 years and lots of money, we would have tested that. We're very aware that different representations lead to different behaviours of these systems. Initial conditions. Kieran made assumptions about the relative proportions of cells at different times. So he had cells flowing into the simulation at a quasi-realistic rate, but again, based on uncertain measurement of real conditions. We had to have a model of time. So Kieran devised a time model that captured the relative differences in time of different biological events, a cell movement model, we had chemical movement models, all sorts. The distributions for random variables, and Kieran has pages and pages of his thesis explaining the distributions that various chemical and adhesion factor rates were drawn from. I'm not going to talk specifically about that, but I will mention a little bit more about those 2 parameters. What makes Alden's thesis and the subsequent papers really interesting to simulation developers is the levels to which he and we went to actually explain our justifications and capture our rationale. And I still find gaps in it every time I look at it. So once you've actually come up with all these models and all these representations, all of which are uncertain, the way that you test is things like calibration, range sampling, and going back to the literature and following things up and talking to the domain experts. Very, very unlike typical computer science testing and validation. Okay, the rest of the talk I'm going to run fairly quickly in very simple terms through the simplifications and the consequences or potential consequences on the key details of the representation. So I've introduced you to the 3 cell types. The second main sort of thing in the system, which is mostly represented as parameters, are chemokines, and chemokines are biochemical things that attract different cells. If these are released into the environment, then they draw particular receptive cells towards themselves, chemotaxis. And in this case, they also stimulate the LTO cells, the cells on the gut wall, to be able to do a binding, a chemical binding. In the model, there are in the domain model, there are 5 sorts of chemokines. These are variously expressed or reacted to by LTAs and LTIs, two types of cells. Again, in the domain model, there's a really complicated description taken from a range of Nature papers and other really powerful, really worthy bits of biology, exploring the biochemistry of adhesion. But essentially it comes down to 3 types of molecule, several other factors that determine how and for how long cells that make contact remain in contact. It's called binding. So there's a really strong understanding of the biochemistry in the domain, but we can't simulate the level of molecular interactions in any meaningful way. So that was what the domain model told us. In the actual simulator, we had 1 agent per cell, so 3 different sorts of agent. The chemokines and the adhesion factors were largely represented as parameter values on those agents. And we had 1 chemokine parameter and 1 adhesion factor. And there's a really strong justification for those. I can't, in the time allowed, I can't go into the whole process of arguing the fitness for purpose. So I've just extracted here in the small text in the boxes the justifications for those 2 simplifications. And I don't expect anyone to read the detail. It's really just proving that the detail exists. But you'll see that 3 of the 4 clauses in these 2 boxes has a reference after it. You can, if you're really keen, you can go to the thesis to find out what the references are, but I think there's a total of about 5 papers from other laboratories cited to justify these simplifications. And it's actually quite a strong justification. When I was going through this, I was thinking, well, actually, there's not much room for uncertainty here. So they've collapsed 5 chemokines down to a chemokine parameter, and they've collapsed all this adhesion stuff here with the alphas and the betas and the VCAMs and the MADCAMs and the ICAMs down to an adhesion factor. So we got a well-justified simplification. Has this introduced simulation uncertainty? Well, arguably it hasn't, because they've done this really careful background research. And at that point, I was feeling quite good about things. But the simulation, although we've only got 1 chemokine and 1 adhesion factor, actually has a lot more in it, because each of these values has a current value for each cell, and it has a threshold for that cell. And then there are rates of change and so on. So although it looks like 2 parameters, there's actually about 6 parameters in there, none of which has a biological equivalent. And in fact, even if we tried to put all 5 chemokines in, we still don't have anything like the biological data to model those faithfully in the simulation. Again, superficially, it looks like measurement uncertainty. We don't know what the appropriate levels and thresholds are. But there isn't anywhere we could go to actually find those. So yeah, it's an interesting form of uncertainty. And just if you want a little bit of evidence, and I will skim through this quite quickly, here's one of those original state diagrams from the platform model. And you can see, if you can see the labels, we've got things like chemokine level triggers chemotaxis or does not trigger chemotaxis. We've got touching RET ligand LTI and binding. So we've got this reference to binding using the adhesion factor, which isn't spelled out. The up arrow on the right-hand side, adhesion insufficient. The L-shape, upside down L-shaped arrow on the right-hand side, adhesion insufficient. So there's a lot more going on than simple parameters and simple measurement problems. So chemokines and adhesion factors control cell movement, cell binding, and the strength and persistence of binds. The levels aren't constant. The mediated behaviours are not deterministic, and there are key threshold values, so we're always having to do comparisons. Again, are these parameter or measurement uncertainties, when people write about how to resolve parameter uncertainties, is this a parameter uncertainty? Some of these questions are just there. So the types of uncertainty that I've illustrated, we can handle those in simulation development. We can use whatever real world data exists with all the caveats that I put on coming from different contexts and uncertainty and not very much of it. We can use our domain expertise, which we use a lot. We can do this calibration activity, modifying the simulation until the simulator produces appropriate results, which always feels wrong to a software engineer. This really is the antithesis of traditional software engineering, where code is tested against an oracle where we know what the expected outcome is. Behavior is tested against objective requirements and the result is Boolean. So we're talking about fitness for purpose, conditional on assumptions, the state of the knowledge, the purpose, and yet to be identified uncertainties. Just summarising that this was pretty much what we did with, or what Kieran did with PPSim. We've done a lot of work on the software engineering aspects since. So we systematically recorded the justifications of pretty much everything. Obviously, there are a few things that will have slipped through our net, and those again are going to be unknown unknowns in relation to the simulator. Systematically calibrated the simulator, and then a statistically based sensitivity analysis, which demonstrated that where parameters influenced simulation behavior, there was evidence that the represented biological concepts were similarly sensitive. That was quite important around some of the chemokines. One of the things that Kieran got his PhD for was the development of statistical tooling and the use of automated scripts to generate and execute variant runs and linking the two together to do the automated analysis. And as I said earlier, thousands, if not millions of runs just to complete the fitness for purpose. Just a couple of slides now. Here are some open questions. There are many more. I'm sure you will have identified many more. You actually need domain oversight for robust calibration or sensitivity analysis, because we may get to a set of behaviours that are producing the right sort of data, but they may be, in our case, immunologically infeasible. Excuse me. So how do we do this when we don't have a good interdisciplinary collaboration with an informed domain expert? How would we do it if we were simulating a complex system that doesn't have a domain expert? In our PPSim, uncertainty ultimately was resolved by laboratory experiments. So there was a lot of uncertainty left, but we demonstrated, or Kieran and his team demonstrated the equivalence of the relevant simulation and the relevant bits of reality. How do we manage to reach that level of certainty if we haven't got that means of identifying key laboratory experiments that are feasible? And I think that the big question, I think this is a question that's been raised in a lot of areas recently, is how do we develop a culture and a practice around deep uncertainty, these inherent uncertainties, that can help other areas of engineering to address complexity or to understand, manage, calibrate, measure uncertainty? And in particular, have we reduced the uncertainty? Has something we've done in a simulator or even in a complex system design reduced the uncertainty of the system in any useful or meaningful way? This diagram is far too complicated for the last slide of a talk, so it's merely to note that we have started to try and link the necessary steps in exploring uncertainty to our cosmos diagram. And if I hadn't nicked this from another talk, I'd have redrawn it so that the boxes match. The top ovals are essentially related to the original cosmos life cycle. We've added in at the bottom left and the top right approaches to exploring uncertainty, and all of these converge on our fitness for purpose. If it's still confusing, read validation activities, and those in turn are tied intimately into experimenting with the simulation and interpreting the simulation results. So that's all I wanted to say. Huge thanks to many people. The box down the bottom is some of the original Cosmos team, which was basically run out of York and Kent, but we had involvement from all sorts of other people as well. So it's barely sufficient to just list these people. Kieran himself, who created the PP simulator, is in the top left. He's a major loss to my research progress. He's now head of operations at the Vianet group up on Teesside. We still communicate and he still approves of most of my research. And then we've got the software engineers, Stefan Shaler from King's, Richard Page and Michaelis Famelis, both out in Canada. Some of you are aware that we've so far failed to produce the post proceedings from the workshop that the three of us ran last year. And then some of the York software engineers who've been involved and influential in this work. So thank you for listening.
Thank you very much, Fiona. Very interesting talk. Other question? I don't see any question in the chat. So, okay, Rogerio raised his hand. So please, Rogerio. And also for the other, you can raise your hand. Okay, Rogerio.
Hello, Fiona. Thank you for a nice talk. All right, it was a brilliant talk. It reminded me the times I was working with John Simmons, actually, quite a long time ago. All right, and I remember the Cosmos project. I still was, I think, kind of with my colleagues here. So my question is actually going to connect two things you mentioned right from the beginning in terms of complex systems, software engineering, ALARP, and the simulations and that you're doing now, right? So the simulations is mostly on the analysis, right? So you try and analyze the complexity, understand the system. But when you start talking, motivate in terms of synthesis, right? In terms of building actual systems, actually, all right? And you can handle uncertainty very well on the analysis. And that's why you've got the simulations trying to understand uncertainty, essentially. But now, when you're trying to map this into a synthesis, all right, you've got a problem there, all right? Because you cannot build arguments, all right, which support our ALARP basis, right? Because it's very difficult to build arguments and build precise evidence, right, of the behavior of the system, right, in order to build the arguments which support ALARP, right? So how you see the gap, because I faced with this several times, how you see the gap of playing or dealing with uncertainty analysis level and actually, all right, manipulating uncertainty at the synthesis level?
It's a very good capturing of what the basic problem is. I mean, I think the systems I'm talking about, the simulations of systems, are as prone to those issues. And of course, the ALARP reference, and indeed fitness for purpose, we were drawing very heavily on safety critical systems engineering there. These are not safety critical systems, but like the aircraft certification, for instance, that goal structuring notation was devised for, we can only make an argument. We had a lot of, because when we were in York, the goal structuring notation, the aircraft certification work was all there as well. So we had endless arguments about whether an argument needs to end in evidence or whether you could just lay out the rationale of the argument. I mean, I can't answer your question, but I can say that the other side of the Cosmos project was looking at engineering swarm robotics. They worked ultimately with Alan Winfield. So it's John Timmis, Alan Winfield, and people in the swarm robotics area. And I think they never they didn't follow the process I've described quite as tightly as the immunological simulations. There are about half a dozen immunological simulations. But they did find that the ideas there were influential. And Alan Winfield, for example, one of his researchers was building, I suppose they would almost be formal models of uncertainty, looking at traces in I'm sure you know you must know the work in swarm robot systems using state machines and so on. So I can't answer your question. I think uncertainty is still in its early days, and I think the validation, I will use the software engineering word, of complex systems designs and models is still in its infancy, except in areas like critical systems engineering, where essentially it depends on really well structured and argumentation and a really strong culture of what is uncertain in the systems. Does that?
No, yes, I would expect that.
As a non-answer, does that work?
No, but it works. No, it's more or less in line with my thoughts. Thank you very much.
Yeah, you are the next one.
Thanks very much, Fiona. That was actually a really interesting talk, I have to say, and very stimulating. One of the things that occurs to me, which I really like your notion that, fitness for purpose is actually a much better term. And I think that it is something that as software engineers, we should think seriously about adopting, because it actually captures far more than just the notion of validation, actually. However, the question I had was really to do with how we can include things like uncertainty into, we have cyber physical systems and all sorts of, systems of systems and so on, as you describe. And one of the ways that we try in most of the things is that we have a domain model, which somehow models the physics of the system and the laws that we understand and know are going to be there. And then what we add on top of that is this layer of assumptions. And we try to say each of these assumptions actually has a rule and a behavior and so on into this model. And these are the things which are uncertain. We don't know whether these are valid or not. And we assume, and we usually have a rationale, as you say, as to why we are assuming that. But of course, it can be violated. And my question really is this actually the best way, in your experience, of going about this? And is there some notion then of testing each of these assumptions? I mean, in your systems, I think you could test some of these against the actual biology. But in other cases, you say, well, we just don't know, so we'll put this in as an assumption and see whether it's violated. Is this the state of the art, or is there something we're missing?
There are other people working in this area. There aren't very many. I think this is still the most open and accessible approach. And I think your observations are absolutely spot on. So Kieran's PhD thesis, he has justifications like the one I put up on the screen, where you go through all the different chemicals and you cite the evidence for why you can get away with only using one. And I mean, at one point I was thinking about discussing those in detail, but I get fried by the immunology, and I'm sure I can't convey it clearly enough not to fry everyone else. Because actually they're subtly different arguments for the chemokines versus the adhesion factors, but both seem to be made clearly and efficiently. when you start looking at testing assumptions, and this is one of the reasons that originally attracted me to working with Kieran on this stuff, he's gone through all those sorts of things. So if he recognizes an assumption, he works out if you can test it, if you can reduce the uncertainty around that assumption, if your domain expert is aware of some evidence somewhere in the literature that would back it up. And each of those is recorded. And interestingly, there's a company that John Timmis, who's mentioned earlier, started, which has a tool for trying to capture evidence in this way. So we've tested this and here are the results, link out to this link, which was based on a tool that we used for our fitness for purpose, which is also now not available because the technology stopped working. So, this has been taken forward. This was a company that was supporting drug discovery, largely doing other things as well. So that systematically going through, the assumptions and the unknowns and so on, and having an account of each. But I think what I was trying to get across towards the end is even once you've done that, well, firstly, you never know that you've got all your assumptions. You're bound to have missed something.
Of course.
And, these PhD-based simulations live in dread of the domain scientists making some fundamental discovery that completely invalidates everything they've done. But secondly, what does that mean? Even, once you've explored everything and put up a justification, and anybody who's looked at your arguments agrees with you, what has that told you? Because the thing is still uncertain. You still don't know. And this, there was a term I used, which I often emphasize a bit more than I did today, right at the beginning, talking about the purpose of simulation. And the purpose is usually quite narrow because you can only be certain about a very small part of what you're looking at. And I think, I think we're still very early in the journey around fitness for purpose, uncertainty, assumptions. I think areas of critical systems engineering often feel that they've tied these down by putting bits of mathematics against them, or having well-defined tools that all link together. But I think we're only touching the surface of a lot of this. There's a long journey to go.
Yes, I can imagine exactly that, and also that, as you say, that you haven't captured all of the assumptions that you need to make.
Yeah.
But there's also a notion, I think, of putting criteria as to what when it is that those will break, and what those things that we need to measure and monitor on the real system in order to see when those assumptions. But thank you very much for.
Yeah, at one point in the Cosmos project, we started writing down all the obvious things. We gave up. I mean, you started with 2D and 3D representations, models of time, different sorts of grid, different sorts of, and then we started thinking about random parameters and different distributions and how you draw things from distributions. And it would have been a great 10-year research program. Yeah.
Thanks very much.
Okay, we can take one last quick question. Colin?
Hi, thanks, Fiona. Fascinating as always. I wondered if you might have any practical advice. This seems to me to be the sort of thing we should be looking at for many autonomous systems. And one of the key things you seem to have done is come up with simple models of agents. And I think it's often challenging for us to think of agents that are simple enough to still be useful. Are there any practical things that you think we should be doing to get there?
I think the most obvious practical thing is be clear what your purpose is. So when you talk to a biologist, you will get right down to physics if you're not careful. You will get 150 overlapping levels of abstraction and trying to tease out what's relevant. So be clear what, this project, but also most of the others that were done in the immunology area, possibly anything up to about 6 months was actually spent trying to work out what it was worth simulating. What real world research question would be answered by a simulation? And that makes the simulation much more targeted and much more focused. So, I mean, it happens in this system that 3 cell types is not a simplification. But there are other simulations where anything involving, if you've ever come across T cells, which actually are involved in a lot of COVID research, so more people have heard of T cells now than they used to. I am not an immunologist, but I vividly remember working with a couple of guys, retrospectively capturing what they were doing so we could learn from it, noting that of the 15 T cell types in the system, and their model has an AT cell in it. And you know, the process that they've gone through convincing the biologists that all these 15 different types of T cell that were relevant to this simulation, that all had subtly different behaviours and effects, that we'd actually taken out all the things that those other behaviours affected, you took part, you know, those other effects, that the rest of the simplification meant that we could do a generic T cell. And then if they wanted to go and work out which of the 15 it was, or whether it was a cumulative effect of all 15, they could go and run the experiment once we told them what the result was. So I think that focus, you know, I think there are 2 really different approaches to biological simulation. There's this one that says, keep as close to the biology as possible and really focus on one purpose. And there's the things like the human heart and brain simulations and so on, which try to create an example system that pulls in all the generic knowledge. And it's not that one's right and one's wrong. A generic heart can allow you to explore the generic behavior of a heart, whereas a 4-day simulation of a tiny part of the gut of an embryonic mouse can tell you precise things that you can test in the laboratory about, you know, really simple bits of cell interaction. It allows you to focus on a laboratory experiment that you wouldn't have been able to, you know, if you'd had to test the whole thing, you would have been doing more experiments than you're allowed to have mice for longer than the scientists were alive. So it's the focusing, it's specific purpose and understanding what research question you can answer with a specific simulation for this type of simulation.
Thank you very much, Fiona.
Thank you, Fiona. Unfortunately, we are out of time. Thank you very much for being with us and for giving us the opportunity to hear you with this very exciting talk. And
thank you very much.
Thank you very much, really. And now we have a small break, the usual 5-minute break, and we will be back for the last session in 5 minutes, so at X48.